We good. All right. Well, I'll get started. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Again, I just pray that you guide our steps today. Help us to glorify you, what we do. And again, I pray the students that if they're struggling, that they would ask questions and get the help that they need, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me get into it. This is, roughly speaking, number 4 in week 13. AKA section 4.6, number 17 for what it's worth. And the problem is this. Find the half-life for a radioactive element with the amount at time t given by a sub 0 e to the minus 0.0333 and t. All right, where t is in years. All right, so we're supposed to find the half-life of this radioactive element. So what does that mean?
You're asking like chemistry terms?
Yeah, I mean, what do we mean by half-life? What's that?
So half-life is how long it takes for half of the element.
How long it takes for half of the element to decompose? Right. So if we had like, for example, if you had like a half of, if you had a kilogram of, let's say, uranium of a particular isotope, then after the half-life of that uranium, you only have a half a kilogram, right? However long that is, or and then a quarter after that, right? Or, for example, neutrons. If you have a free neutron, its half-life is about 11 minutes. So if you had 100 free neutrons sitting out there after 11 minutes, you only got 50. The other 50 have split into a proton and an electron neutrino, or something like that. So, so what we're looking for is the time when we have a sub 0 over 2. See, because a sub 0 is what? Notice that if we plug in time 0, what do you get? We get a sub 0 e to the 0, right? Because minus 0 is still 0. And what is that? Well, that's just a sub 0, right? So the amount at time 0 is this constant a sub 0. So we're looking for the time when the amount has dropped to a sub 0 over 2. And the interesting thing, of course, among others, is that the amount doesn't matter, right? You can divide. You didn't need to know the amount, did you? So we just divide. And you got 1/2 is e to the minus 0.0333t. And now we got to solve this equation, right? So that's why it's in chapter 4 in section 6, because this is an application of logs and exponentials, right? So we need logs and exponentials to solve this thing. How are you guys going to solve it? How would you? I heard a vote for taking the natural log of both sides. I like it. Let's try that. Natural log of 1/2 is natural log of e to the minus 0.0333t. That simplifies to minus 0.0333t. And now I can solve for t. So what's t equal to? My t is equal to the log of 1/2 divided by minus 0.0333. So let's work that out. You plug it in your calculator, and what you get is about 20.81. Now, if you read the answer, read the problem. This problem says round to the nearest tenth of a year, right? So the nearest tenth of a year is 20.8. 20.8 years would be the half-life here, right? So So that's essentially number 4 in week 13 homework. Let's try another. Sample 2, you got 12 grams initially, and then after a little bit, 6 grams remain after 7 years. And the question is, how much of this radioactive element or substance, you could say, remain after, get this, 18 years? So that's the question. So the math here, it's the same mathematical model as the last problem, right? It's still governed by that same equation, basically. But here the data is different. I mean, one thing I can tell you right off the top of my head from this problem, you're dropping from 12 to 6, right? What's the half-life for this one?
7
It's 7 years, right? 7 years, it's just given to you. Essentially, the half-life is 7 years, yeah? And so if I went to 14 years, how much would remain? 3 grams would remain after 14 years. What if I went to 21 years? 1.5 grams, right? So I expect that the answer should be somewhere between the 14-year mark and the 18-year mark. So I expect my answer is somewhere between 3 and 1.5 grams, right? But that's not an answer, right? That's just a range. So unfortunately, the time we're asked about doesn't land in one of the doubling times, you know? If the time was a multiple of 7 years, this problem's really, really easy. But it's not, right? So we got to work it out. So what we know is that, generally speaking, A of t is A0 e to the minus kt. So the question then is, what is the A0, what's the k and everything, right? Well, hey, we know A sub 0 is 12, don't we? That was given to us. So we know that A of t is 12 e to the minus kt. What else do we know? Oh, yeah, we know that 6 is equal to 12 times e to the minus 7k, right? Because of this I know, because this I was given, all right? So solve for k. Because once you solve for k, then you know a is a function of t explicitly. Can we solve for k? Take the natural log? Sure, but first let's divide by 12. So divide by 12, we get what? We get 1/2 equals e to the minus 7k, right? Divide by 12, yeah. I lost the other class with that step. Are you guys okay? Are you sure? The mean girls are okay. Okay. All right. All right, then what? Natural log of a half. All right, natural log of both sides. Oh, yowzers. Natural log of 1/2 is the natural log of e to the minus 7k, which gives me, well, you know, natural log of a half is minus 7k, right? So k equals 2. Natural log of a half divided by minus 7. What is natural log of a half, by the way? It's bothering me. I have to say it at some point today. That's minus log 2, yeah? So really, you just got log 2 divided by 7. Listen, it doesn't cost you much more time to just plug log of a half into your calculator. I just feel like I should say it at some point today. I've been forcing myself not to say that all this time.
Question. So
Try not to divide.
Natural log of 1/5, would it be minus 9?
Yeah, log of 1/5 is, yeah.
Okay.
And any fraction, 1 over n is minus log n.
Okay.
Yep. Because it's to the minus 1 power. So let's see here. So we've got log 2 divided by 7, and that gives me, oh, here we go. All right, come on. Come on, marker. Come on. There we go. 0.0. I'll give you 4 digits. 9902. All right. 0.9902, approximately, of course. And so what's my formula?
5 digits.
Well, you know what I mean. Fine. It's 5 digits. You got me. All right. Fair enough. I was caught. I've given you too much. Fine. There. No, fine. I'll put it back. I'll put it back. Sorry, I'm easily amused at this time of day. So A of t is, what was it? It was 12 e to the minus 0.09902 times t. Okay? What am I looking at? What am I looking for? I'm looking for the amount after 18 years, right? So now I have to plug 18 into this formula. So what's A of 18? 12 times e to the minus 0.09902 times 18, which gives me what? Give me a second here, I'll tell you. I get 2.019, right? By the way, this is all in grams, yeah? So what's the answer? Well, it depends on the wording of the problem, right? So here it says, it wants thousandths, apparently. 3 decimal places is needed, so, oh. Yeah, I just already did that. The answer actually in my calculator was 0.20. It actually says to keep 7 decimals throughout the calculation in the instructions, which I have not been quite following the instructions in that regard. Anyway, so 2.019 grams is the answer, which is where I predicted it would be, right? Somewhere between 3 and 1.5. But to actually find the exact amount, we have to do the math, and that's just what it is. Yep.
Do we have to divide that by 18 to still have A?
No. That's A of 18. That's not A times 18. This is the function A evaluated at t equals to 18. Like that's a good question because, listen, somebody else asked me in another section the following question. We had natural log of x squared like equals to 7. And I said, how would you, or natural log of x equals to 7, something like that. And they asked me, I said, how would you solve for x? And they said, I would divide by ln. See, and that's the, like, I mean, that's not crazy. That's not, it's wrong. It's really, really wrong, but it's also not insane because we've been manipulating symbols with that meaning up to this point, right? But we have to think about, this is function notation, right? So this is the function A evaluated at the input, right? And this is also function notation. It's the natural log function evaluated at that endpoint, which is really obnoxious because we use the same notation, right? For like 13x squared plus x. And that doesn't mean, I mean, well, I don't know. I just, x equal to y? F of x equal to y, yeah. Right. I mean, computer scientists have all kinds of special notation to make these things rigorous in terms of things I don't care about. But anyway, yes?
So at the bottom says k equals the natural log of 1/2, and then it goes to negative natural log of 2. How do we get from the first one to the second one?
See, this is why I haven't said this yet today. All right, so it's just log of 1/2 is what? Right? Now, did I need to make that step? No. Was it distracting? Manifestly now, yes. So, but Because we could have just plugged a log of a half into the calculator just the same. I mean, but if you, it's an important simplification to know about in the world of simplifying logs, you know, but I could have stayed in my lane and not done that in this problem and not be having this conversation right now, which is a good conversation to have, mind you. It's just, eh. I had the discipline to not prompt that conversation up to this point today, so, you know. Okay, example 3. Any question, or
We seem to prompt.
what?
Push your buttons.
I just misbehave in here more, because you guys are more fun. Don't tell the other class.
I think they see the video anyway.
No one, the other classes aren't watching this video. Do you guys watch the class of the other video to find out how I talk about you in there? No, right?
That's too much work.
That's what you think.
Yeah, that's what I think.
You think we don't watch.
That's what I know. I count the views every day.
Watch the video.
I watch the view count. I'm like, nope, nope. I study it. I have a GA assigned for the analytics. Okay, that's a lie. I don't have a GA.
You have an
And
algorithm.
I wouldn't know where to find the analytics if I wanted to.
You have an algorithm for it.
Okay, so here, example 3, which will be number 7 in the homework, yeah? And here you're given f of t is t sub 0 plus c e to the minus kt. This is so-called Newton's law of cooling. And so Newton's law of cooling has a formula that looks like this. Here, this is the room temperature or ambient temperature. All right, and we're given more information. So this problem is about a cup of coffee cooling off in a freezer. All right, so you have a cup of coffee, and it's originally at t equals to 0. It's at 140 degrees Fahrenheit. All right, that cup of coffee is put in a freezer, a 0-degree freezer. So the freezer, you put the coffee in the freezer for reasons I don't fully understand, but you put the coffee in the freezer. So this is a 0 degrees freezer, right? And you're given other information. You're told that after 10 minutes, the temperature is 62 degrees Fahrenheit. At t equals to 10, you have 62 degrees Fahrenheit coffee. All right. Then what's the question here? The question is to find the coffee's temperature at 15 minutes. What's the temperature at 15 minutes is the question. So there's the problem. How are we going to solve it? Yes, I've got to solve. I've got a problem now. I'll solve it.
Oh, we have T, right?
Tea? What?
We have T.
I have tea.
When you find,
No, it's coffee. It's coffee.
when you change MTs with like final temp minus initial temp,
Hmm.
you
Well, I'm told that T0 is the room or the ambient temperature, so let's start there. So that means that the T0 is what? So it's where the coffee is. So by the application here, the T0 is 0 degrees. Now that makes sense. Like if we think about the formula, as time goes to infinity, this piece drops to 0. All right. And so you're just left with T0 for a long, long time. So what that means is that eventually the coffee gets really, really close to 0 degrees Fahrenheit, right? In fact, this formula doesn't really make sense long term, because what happens is the coffee freezes, right? And then the coffee isn't just approaching 0 degrees Fahrenheit, it is 0 degrees Fahrenheit, right? When you have that phase change. And when there's that phase change, this equation ceases to be meaningful. So this is an approximation. It's our best description of how temperature couples between objects macroscopically. And it's a pretty good model. What it says though is that, well anyway, enough about that. So we figured out T0 is 0. Great. So we have, by the way, f of t is the temperature, right? So f of t is c e to the minus kt, yeah? So that, we use that. What can we use? Well, we also know that t at time 0 is 140, right? So 140 is the temperature at time 0, which is c times e to the 0, also known as c, because e to the 0 is 1, right? So this shows me that c is equal to 140. Good grief. So f of t, apparently, is 140 e to the minus kt. All right, so I've used the freezer temperature being 0. I've used that the initial temperature was 140. What have I not used yet? What piece of data have I not used yet? Right, I have not used the coffee 62 degrees after temp. So that's the remaining piece of the puzzle here, right? So how do we use that? What's that mean? How does that translate into the model that's given? That means if we plug 10 into the temperature function, we get back out 62, right? So if we plug 10 into Newton's law of cooling here, we get 62 is equal to 140. I keep writing 140 as 114. Now it's wrong with me. 140 e to the minus 10k. We don't know k yet, but we'd like to. So can we solve for that? This problem requires patience, right? If you try to solve immediately for what you're looking for, you can't do it. You have to take this problem one step at a time, like just being greedy and going, I know, I don't care about k though. I want to know what the coffee temperature is at 15 minutes. Like if that's your approach to this problem, you'll never get through it, right? You have to be content to take baby steps towards that goal, yeah? So you just keep chipping away at it and finding things you don't know and putting it together. Eventually it comes together. So what do you guys say? How about divide by 140, right? E to the minus 10k is equal to 62 over 140. Take the natural log of that thing, what do you get? We get minus 10k equals the log of 62 over 140, which gives us k is equal to log of 62 over 140 divided by minus 10. So what's my k? What is k? Like conceptually speaking, k here describes how the coffee cup couples to the freezer, right? Like the specific value of k is going to depend on the geometry of the coffee cup. Is it an insulated cup? Is it, does it have a cover? All these kinds of things, right? Different coffee cups will cool faster or slower in the same freezer, right?
Yeah, those are some factors that we're not.
But the interesting thing about Newton's law of cooling is it basically says all those factors being, whatever, ignoring all those factors, it's always about the same pattern, It's always just this formula. So I get 0.08145508. I'll keep that many for you guys. So there's my k, okay? And okay, so then, okay. Sorry, it's there. I can't refuse the joke, it's just there. F of t, 140 e to the minus 0.08145508 t. All right? And then what was the whole question, though? The question was, what's the temperature of the coffee at time 15, right?
Wouldn't it be 39?
Now we have to plug it in to that. Wouldn't it be just 39? Why do you say that? Because it cooled, what? This was 140 minus 62, which is like 80-ish. And then you're like, so if it so divided by 2, it should cool another, what do you say, 40? No. This from here to here is 80. So every 5 minutes it cools 40 is your point?
Yeah.
So you think it should be 20 degrees? 39. Why do you say 39? Oh, 62 minus 20. Right? So 39? Let's see if it is. I don't think it will be. E to the minus 0.0814508 times 15, yeah? Times 140. It gives us 41.26. And then we're told to round to the nearest degree, I think, in this problem. So what's the nearest integer? Nearest integer here is 41 degrees, yeah. So what the idea that Francisco was trying to use is that the drop in temperature is linear. That for a given amount of time you get a given amount drop in temperature, right? But that's not how this works. Like, for example, I guess you can see that already, right? So like, in the first 10 minutes, we drop what? About 140 minus 60, which is like 80. Yeah, 78 degrees in the first 10 minutes. We drop 78 degrees, right? And in the next, so I guess to be fair, we should figure out what is the temperature at time 20. I don't want to do that. Let's see here. Anyway, so the point is, in the first 10 minutes we dropped 78 degrees, but then in the next 5 minutes we only dropped an additional what? 21 degrees, right? Which is not just half of, it's not half of 78, right? Not remotely. We dropped a lot more, proportionately speaking, in the first 10 minutes than we did in the next 5 minutes. And let's see here. We could look for, here's a question. When does the coffee reach a temperature of, oh, I don't know, 20 degrees? When is the coffee 20 degrees? Can you guys tell me that? How would you, that's a good follow-up question to the, your homework doesn't ask you that, but this is a good follow-up question, you know, certainly a reasonable question for like a, what are those things called? Quiz, test, whatever. How would you figure this out? So what I've been told in previous sections is, oh, plug 20 into the formula. This makes no sense. 20 is not a time. You don't plug temperatures into the formula. T is time, right? We don't know T. That's the whole question. What is T? What we do is we put 20 equal to the formula, which is 140 e to the minus 0.0814508 time we don't know, and solve for T and see what time that is. Yeah? We know it's going to be a time beyond 15 minutes, right? You could speculate, when do you think it's going to happen? Time 20? Well, I mean, there's no, we'll just have to work it out, right? So 20 over 140, e to the minus 0.081, I'm done with it, 815t. Tired of all these stupid decimals. I don't know why I'm keeping so many digits on that stupid thing. And so we've got the natural log of 20 over 140. 20 over 140 is what? That's just 1/7? 1/7? So the natural log of 1/7 is equal to minus 0.0815t, which gives me t is equal to, you know, natural log of 1/7 divided by minus 0.0815. What do we get? What'd you guys guess? 22? That's not bad. It's actually 23.9, roughly. So it takes another, let's see here, it takes about another 9 minutes for the temperature to half from 41 to 20. Something like that. So a silly application of this I've been sharing with the other classes is like, if you think about, adding cream to a cup of coffee, if you want to keep your coffee hot, should you add the cream right after you make it, or should you wait to add the cream later when you drink it, if you want your coffee to be hot? Most of you are like, I just add the cream so I don't burn my mouth, right? I mean, that's the common answer I've been given, which is accurate. It's how it is for me anyway. But the answer is you should put the cream in right at the start, because what that does is it lowers the temperature at the start, right? Which then makes the difference between your coffee temperature and the room temperature smaller. All Newton's law of cooling basically says is that the difference between, like the temperature changes faster the larger the difference is between the coffee temperature and the room temperature. So you're going to have to lower the temperature putting cream in eventually, right? You're going to lose less heat if the coffee starts out at a lower temperature after you put the cream in, everything else being equal. So anyway, and you can kind of see that in these numbers if you think about it. But all right, moving on here. What's next? Money. Money, 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 money. Example, did we get over here? Okay. Example, where am I? 4? Thank you. You got an investment. Investing at 8% continuously compounded. How long to triple your money? This is essentially number 8 in the week 13 homework. All right, so the question is, what's the formula for continuous compounding, right? And so one of the reasons people are excited about the exponential is this reason. So the formula for continuous compounding is this. P of t is equal to P0 e to the RT. So that's the formula for continuous compounding. All right. It can be understood as like the limit as the number of compounding period goes to infinity. You can see the exponential as appearing in that way. But anyway, it's kind of, I'll leave that for calculus. Here, what are we looking for? We're looking for the time when you got what? 3 times your initial money, right? P0 is your initial investment. So how do I solve that? That gives me e to the RT equals to 3. Now, an important thing to know about here is when we say 8%, that is understood to be a yearly rate. And mathematically, what that means is that this variable r is not, it's not 8, right? R is not equal to 8. This means that your r 0.08. That's how that works, okay? So what we have is we have e to the 0.08 times t equals to 3, and we just need to solve that for t. How do you solve for t? I think the answer to every algebra question I pose today is you take the natural log, right? So we take the natural log. And we get 0.08 t equals log 3, which gives me t is log 3 divided by 0.08. At which point I need to get my calculator. And we get what? $13.73 years. Unfortunately, this problem makes no sense at all because there's like 12% inflation right now, so whatever. But, you know, ignoring that, it's a lovely problem. So. Oh, the stock market, yes. Okay, so listen guys, that's a pretty good cross-section of the word problem homeworks. There are more in your homework that are word problems. I'll let you look at those. Like, I'm deliberately skipping over the mummy problem, the bacteria problem, the number of people with the disease epidemic problem, the random formula for the height of a certain tree problem. You know, all of these have a uniting feature. Every one of them gives you the formula in the problem, all right? So you have to look at the formula in the problem, you have to look at the data you're given in the problem, and suitably apply that data to make sense of the formula and answer the question. So it's pretty much the same thing we've done for every one of these examples, except for the last one. The last one, I had to pull from the thin air, right? The formula P equals, you know, P of T is P0 e to the RT. But, you know, this is in your book, which you guys are all reading, right? Yeah, okay. But otherwise, the formula is supplied in all the other problems. So it's going to be the same song and dance. Now, if you get stuck on those, we can talk about them in another class. But I'm going to go on here because I think it's important for us to start our discussion of systems of equations. All right, so let's get on to that. So today, I will talk to you about two equations and two unknowns. So I always start the two equations, two unknowns discussion with just a quick graphical kind of overlay. And so here it is. What is two equations and two unknowns anyway, right? So two equations and two unknowns, something like this. ax plus by equals to c, dx plus ey equals to f, where, you know, ab is not equal to 0. Well, I can't say that. That's not the way to say it. But A, B, C, D, E, and F are numbers. They're real numbers. And both A and B and D and E are not 0. I'm still not saying that, right? Let me just say it in words and not try to write it in a sentence. I don't know. There's a quick and painless way to write this, but I haven't thought of it yet. I don't want to allow both A and B to be 0. That's not a good faith linear equation, all right? And I don't want to let D and E both be 0 either. That doesn't, I shouldn't allow that, all right? So I'm insisting that at least one of each of the coefficients of x and y be non-zero. That's probably how I should write it. At least one of A, B, and at least one of D, E are non-zero. So that these are genuine linear equations, right? So since these are genuine linear equations, this is two equations and two unknowns. What's their goal? What are the unknowns? The unknowns here are x and y, right? So because they're x and y, we can visualize this problem in terms of like a graphical understanding, right? Each equation corresponds to a line. So we're looking for a solution which means that point is on both lines. So we're really looking for the intersection point of both lines. And so if you think about that, there are three cases, yeah? So generically speaking, let me just draw my line like this. My first equation, there you go. First equation has this line, right? Now what are the three cases? How about the second equation? It could look like what? It could look like this, right? In which case the solution is this point of intersection, right? This is case 1. Case 2, right? Well, you could have the other equation is actually like a parallel line, right? In this case, there is no solution, right? So this would be a unique solution, right? And the solution is whatever that point is. Here, there is no solution. No solution. This is solution. You probably already knew that. And what's the other case?
Is it where it's the same line?
Where it's the same line, right? This is kind of conniving, but it's possible that both equations are actually the same line. And in this case, there's infinitely many solutions. Well, remember the solution is a pair. So it's a bunch of pairs, but they're of a really particular type, right? So here, example 1. Well, what example am I on? I guess I'm on example 5. All right, so example 5, I'm going to make it really dumb. Suppose your system is this. X equals to 2, y equals to 3. Right? Graphically, what's going on there? X equals to 2 is this line. Y equals to 3 is this line. The point of intersection is what? Right here, right? So the solution is 2, 3. Example 6. We could have something like, x, or we could have minus x plus y equals to 0, minus x plus y equals to 1. So what is minus, so these, let me put them in a more familiar framework, yeah? That's y equals to x, right? And this is y equals to x plus 1, right? And so, sorry, graph that. You've got two lines. They each have slope what? Slope 1, right? Y equals x. This guy. Y equals x plus 1. This guy. That was supposed to be parallel. I tried. Anyway, my point to you, there's no place that's common to both of those lines, right? No solution to these two equations. Right? There's no simultaneous solution of both equations. Example 7. Let me put it over here. Well, fine, I'll put it here. You could have, really silly, x minus y equals to 0, 2x minus y, 2x minus 2y equals to 0. See, it looks like two equations and two unknowns, but truth is, to get the second equation, you just do what to the first? It's just what, really? Just multiply by 2, right? So they're not really independent equations. Truth be told, it's the same equation written twice. And what's the solution? Well, I mean, graphically, it's everything on the line, So this line is just y equals x, yeah? So my solution is what? So this time I really do need the solution set idea. Solution set, it's x comma y such that, well, y equals x. And we can make that a little bit better. Like I would prefer to write that solution in terms of a single parameter as follows. I would write it like this. This is x comma x such that x is a real number. So this is the case 3. This is the case that the solution set is infinite. What's the solution set in example 5? It's very silly, but the solution set over here is what? It's the set containing the point 2, 3. It's really obnoxious, but there's the solution set in this case. All right, so, oh man. How many more minutes do I have, guys? As long as I need. They'll meet you in the hallway afterwards for your beating. What's that? You said 4? Okay. Now, oh man, up to this point, we haven't needed anything really tricky to find solutions here, right? They just were just kind of obvious graphically for us why the solutions were. Let me work one example here for today. Excuse me. Where we can't, probably graphical method is a bad idea. So 3x minus 7y equals to 13. And let's say x plus 10y equals to 9, right? There are 3 ways I know to solve this problem. All right? The one way is graphical. Get out a piece of graph paper, graph both of the equations, find the point of intersection. This is straightforward. It's very satisfying in a certain regard, but it's also tedious and inaccurate, right? So what's a better way? Substitution is the next. Yeah, substitution, and the other thing is elimination. That's right. But we're going to do substitution to start with here. So substitution, the idea here is to solve one of the equations for one of the variables and plug it into the other. Which one should I solve for? It's just yelling at us. Solve for me. The bottom one. And solve for y, right?
Yeah.
Don't believe that. That was a trap. Solve for x. Solve for x. So we get x is equal to 9 minus 10y. And I usually like to number my equations so I can be accurate here. So from 2, we get that, right? And then plug x equals to 9 minus 10y into 1 to obtain. What's that give us? 3 times 9 minus 10y minus 7y equals to 13. And then what? Now I have one equation and one unknown. And back to a simpler time, the first week in this course, when we first saw this problem, right? At the very end of the first week, maybe? Actually, we did uglier stuff before we did this, didn't we? This came after we did harder things, weirdly enough. But anyway, so 27. I should start with this in this course. But anyway, minus 30y minus 7y equals 13. So what you got? You got 27 minus 13 is what? 14, I believe, equal to 37y, if I did my math right. Which gives me y equals to 14 over 37. All right, well, that's half of the story. What's x equal to? Plug in.
Isn't it minus 37?
Minus 37?
Minus 30?
Because
Minus
you
7?
moved to the other
I moved the other side. So x is equal to 9 minus 10y, which is 9 minus 140 over 37, which is 9 times 37 minus 140 over 37, which is whatever that is.
You lost it.
I lost you.
No, where's the 140?
14 times 10. That is 193 over 37. So lo and behold, the answer is 193 over 37, comma, 14 over 37. There you go. That is the answer to this system. That is the point in the plane where those two lines intersect.
Can you grab that one?
If I had to graph that, we'd be here all day, right? Like that would be, I mean, isn't this, I mean, I don't think we appreciate this enough.
Yeah.
This would be really hard to figure out graphically, but this algebra that we just did, it wasn't that bad, right? And we found something that's actually really, really picky. This is what separates us from Euclid. Like in Euclid's time, a lot of people, they didn't know about this way of thinking, right? They didn't have equations for lines. They just had, you construct lines with straight edges and compasses. The idea of using an equation for a line to model it, that's much later, like Descartes and well, these Cartesian coordinates. It's, you know, it's like a 15th, 16th century kind of thing.
They figure stuff out.
Anyway, thanks. You got it?